Hello everyone, I'm Jiang Jiaxin. Today I'm going to present a framework which addresses real-time fraud detection on evolving graphs. The framework is called SPADE. Let's begin by outlining the key component of our presentation. I will start with the background of our research, then I will introduce the problem statement, followed by a detailed exploration of the SPADE framework. I will introduce peeling sequence reordering techniques. Finally, I will present insights from our experiments. Transaction graphs, as we know, are dynamic. The sudden appearance of suspicious activity with this graph can lead to significant economic losses. This forms the core of our motivation to prevent such losses through real-time fraud detection. Our first challenge is to answer the questions: can we identify fraudsters in real time? The operational demands of the industry require us to detect fraudsters within 100 milliseconds. This challenge emphasizes the need for rapid fraud detection mechanisms. Our second challenge is equally important. Can we propose a generic framework that's incrementalizable? The reality is that training all developers with the knowledge of incremental graph evaluation is impractical. So we aim to develop a framework that streamline incremental processing while maintaining efficiency and accuracy. Let's explore a graph pipeline for fraud detection. First, there is a graph construction where we have the foundation for analysis. Then graph updates are performed periodically. The heart of the process lies in fraud detection, where our SPADE framework comes into play. Finally, actions are taken based on the detected anomalies. However, even with this pipeline, there are limitations. Fraudsters are detected only at T2, leaving a gap between T1 and T2 where significant economic loss might occur unnoticed. This highlights the need for early detection to bridge this gap and prevent potential fraud activities. Therefore, we aim for early detection of fraudsters at T1, bridging the gap and preventing economic losses. Also, we aim to create a framework that supports incremental processing. Let's move to the technical details. The density function denoted as GS quantify the relationship within an induced subgraph GS composed of vertex S and HES. GS is defined as the ratio of the sum of suspicions of S and ES to the size of S. AI represents the suspicions of a vertex UI, while Cij represents the suspicions of an edge. This term demonstrates the decrease in the value of f when vertex UI is pure from S. The peeling sequence involves peeling the vertex with the smallest peeling weight. This results in series of sets over V denoted as Si. Our peeling algorithm finds the set Si that maximizes the density matrix GS denoted by SP. The complexity of the peeling algorithm is OE log V. Furthermore, the algorithm offers an accuracy guarantee. GSP is guaranteed to be greater than or equal to half of GS star, where S star represents the optimal vertex set. For example, the subgraph in the red rectangle is the optimal vertex set. Here is our problem. Given the graph G and the peeling result SP, we need to efficiently determine the peeling result when applying the same algorithm Q to an evolving graph resulting from graph updates. This evolving graph is represented as G O plus delta G, where delta G represents the graph updates. Now I will introduce the core feature of the SPADE Framework's API. The SPADE Framework's API includes several key features designed to enhance its capability. We have enhanced the suspicionist function for both vertex and edges. SPAD also offer better control over the streaming model. Insert edge handles individual edge insertions, while insert batch edge optimizes the insertion of multiple edges, contributing to efficient processing. The SPAD framework provides three crucial metrics to evaluate the efficiency and effectiveness. A key strength of the SPAD framework lies in its ability to incrementally evaluate evolving graphs. We have introduced pinning sequence reordering techniques that optimize this evaluation process. Our framework also use edge grouping to reduce the latency and queuing time and increase prevention ratio. Next, I will introduce how to do pinning sequence reordering with edge insertion. There are three cases. In first case, if the edge insertion priority of vertex whose pinning weight delta mean is smaller than that of vertex UK, two actions take place. We pop vertex U mean from the top of the heap T and insert it into the order set O prime, such as U2. We update the priority within the heap T for the neighbors of the vertex U mean. In the second case, if the edge insertion priority of vertex U mean is greater than or equal to that of vertex UK, and UK has some neighbors within the heap T, we insert UK into heap T, such as U2. For the last case, in the event that edge insertion priority of vertex U mean is greater than or equal to that of vertex UK, and vertex UK has no neighbors in the heap T, we insert vertex UK into the order sequence O prime, such as U3. The time complexity of this process is bounded by O E log V. This complexity ensures efficient execution while optimizing the pinning sequence and enabling real-time processing. Let's explore the pinning sequence reordering in batch. An interesting challenge arises when the pinning sequence reordering through early edge insertion could be reversed by later insertion. This results in some reordering become stale and even duplicate. To solve this, we introduce a novel approach, reordering in batch. We first conducted a vertex sorting of delta V. The vertex sorting is a key concept here involves the lemma. Then we consider three cases. In first case, we follow the same step as previous discussed. And the second case, if vertex U mean has an edge insertion priority greater than or equal to UK, and vertex UK has some neighbors in heap T, we insert vertex UK into heap T. For the last case, if vertex U mean has an edge insertion priority greater than or equal to UK, and vertex UK has no neighbors in heap T, we insert vertex UK into order sequence O prime. We then append the raised elements O, K, I prime minus 1 to the order sequence O prime. Next, I will introduce pinning sequence reordering with edge grouping. We first define the benign edges insertion UI and UJ and denses subgraph. When dealing with a benign edge insertion represented as UI and UJ, it is important to know that neither vertex UI nor vertex UJ belongs to the densest subgraph. Additionally, this insertion cannot lead to creation of a denser fraudulent community through pinning algorithm. One of the key advantages of utilizing the SPAD framework is its ability to perform a batch update. This approach ensures that computations remain fresh and avoid becoming stale, so enhancing overall efficiency. When an urgent edge insertion coming in, triggering incremental maintenance become a priority. The SPAD framework is designed to address this scenario by immediately handle the required incremental updates. This low latency ensures that the framework remains responsive even in dynamic environments. Next, I will go through the experimental setup we employ to evaluate the SPADE framework's performance. For our evaluation, we utilize a diverse set of dataset, combining both industrial and open source data. Our implementation was memory resistant and written in C++ for optimized performance. Let's discuss the baseline and proposed algorithm that form the foundation of our study. DG, DW, and FD are the algorithm which approach the problem by detecting fraudulent community from scratch. Building upon the baseline, we introduce our set of proposed algorithms designed for incremental processing. ENC-DG, ENC-DW, and ENC-FD they optimize performance by adapting to evolving graph through incremental updates. We denote the algorithm with the batch update as ENC-DGX, where X represents the batch size delta E. In addition to the proposed algorithm, we explore the concept of edge grouping denoted by ENC-DGG, ENC-DWG, and ENC-FDG. We kick off with a comparison between DG and ENC-DG. ENC-DG is 4,000 times faster than DG. For majority of edge insertion, only a minor portion of the peeling sequence is affected. ENC-DW is 1,000 times faster than DW. During edge insertion with relative large weights, we observe a notable impact on the peeling sequence. ENC-FD is the sixth order of magnitude faster than FD. For the majority of edge insertion, there is no effect on the peeling sequence when using ENC-FD. Now let's explore the impact of varying batch size delta E. ENC-DG 100K is 1,000 times faster than ENC-DG. ENC-DW and ENC-FD has similar performance improvement. As we increase the batch size delta E, we observe a consistent trend across this algorithm. The running time for an edge insertion decreased. An important insight emerged regarding the reordering of the peeling sequence by early edge insertion and the potential reversal by later ones. By reordering the peeling sequence in batch, we reduce the probability of such reversal. Let's go through the importance of employing edge grouping on the performance of our incremental algorithm. ENC-DG is 7 times faster than ENC-DG, and the edge grouping techniques typically accumulate more than 1K edges. This observation is in alignment with the characteristic of real-world graph, where benign edges insertion tend to dominate. Real-world graph often adhere to the power law distribution. Let's go through the impact of edge grouping on latency for our algorithm. Here is the latency comparison for 3 algorithms. For ENC-DG, ENC-DW, and ENC-FD, 99% of the latency is attributed to queuing time. This latency ratio highlights how edge grouping substantially reduces the queuing time, consequently minimizing the overall latency for our incremental algorithm. Let's go through the impact of the next, I will introduce the relationship between latency and the prevention ratio. As we introduce the batch size, the latency of the batch peeling sequence also increased. The observation indicates a trade-off between the size of the batch and the latency of the algorithm. Our results prove the effectiveness of edge grouping. This algorithm stops up to 92% of the fraudulent activities. Let's explore some case study in discovering meaningful fraud patterns by SPADE. We can find customer merchant fraud, deal hunter, and cliff farming. We take a DG as an example. In the case of the potential fraudulent transaction, SPADE prevent 700 transactions, highlighting it is effectiveness in detecting fraud. This case study underscores SPADE potential in identifying a variety of fraudulent activities. In conclusion, SPADE stands as a pioneering real-time fraud detection. We introduced 3 foundational pinning sequence reordering techniques. And we also have some experiment improvement. And also we have some promising direction for future work. First one is the edge insertion and deletion. And second one is the expanding sped compatibility with a broader flaw detection algorithm will further broaden its utility. Thank you for your listening. Any questions?